All right. Okay, so I got 4 more questions for you, and then hopefully we'll get out of here on time, hopefully within the next hour or so. Okay, so we're gonna continue on with our random processes and power spectral density stuff. So we have a white noise process, okay, so it's gonna be a height of, n0/2 or whatever that height will be, okay? And then the input of this process is into a LTI system or a channel with the following transfer function. Okay, so we have this transfer function here. Also, we're gonna practice this in terms of omega this time. So let's actually take a look at what this would be in omega. So remember, omega is just 2 pi f. So this becomes 1 plus, and then let's see here, j omega rho. Okay. So remember that omega is equal to 2 pi f. Okay, that's great. Okay, so this would be the transfer function of your channel. So you're going to put your white process into this communication channel, and then you're going to filter based on that. So, and then rho is a constant. So the input process has the following characteristics. So we see that the mean of the random process is 0. Also, the autocorrelation function deals with the time lag itself, and that's actually good. So this is actually a true additive white Gaussian noise process, which is nice. Okay. So the corresponding output is going to be y of t. So what they actually are doing is that you have this process that goes in, right? So this is h of f, right? And the output is y of t. So that's basically what's going on here. So you have to figure out what the output power spectral density is, what the autocorrelation function of the output is, and finally what the output power is going to be. So this is actually not bad to do. It's going to require a little bit of trickery, but nevertheless, it's actually very simple to do. Okay. And then this here, actually we'll do it in omega this time, not f. We're gonna do some practice. So this becomes 1/1 plus j omega rho. Okay, so first question, output power spectral density. So we are given the autocorrelation function, okay, is equal to sigma squared delta tau. All right, so if you remember what the equation was for the output, so we have to figure out what this is. Right? It's basically taking your the impulse response of your LTI system. So you basically take whatever the magnitude is squared and multiply this by the input, power spectral density. So we don't actually know this yet. So we have to figure out what this is. We're given what the autocorrelation function is. So if you want to figure out what the power spectral density is, you just simply take the Fourier transform of your autocorrelation function. Okay? So if you remember, the Fourier transform of an impulse function, right, is simply a constant. It's just equal to 1, okay? So in this case, if you want to figure out what the power spectral density is for this, it's just simply sigma squared, okay? So that's pretty much what it is. So remember, the Fourier transform of an impulse is just simply equal to 1. So if you transform this, it's just simply equal to that times 1, which is fine. So that's what we have here. So, so we have this piece of the puzzle. Now you have to figure out what this is, what the magnitude of this is. So here's a little trick for you. So if you want to figure out what the magnitude squared of an impulse response is, all you have to do is just take the normal transfer function and multiply it by the conjugate. Okay? This actually boils right back down to complex numbers in linear algebra. Okay, so if I had a complex number, a plus jb, then if I multiplied it by the conjugate, which is just minus that, if you actually work this out, this becomes a squared plus b squared. Okay? And if you remember the magnitude of a complex number, so let's call this I guess e, all right? Okay? And if you want to figure what the magnitude of the complex number is, it's just simply, square root a squared plus b squared, right? So if you want to figure what the magnitude squared is, right, all you have to do is just get rid of, the square root, and you're left with just, okay? So if you want to figure out what the magnitude squared is of a value, all you have to do is just take the number and multiply it with its conjugate, okay? So in this case, we have 1 divided by 1 plus j omega rho, and then you multiply this by the conjugate. So when you do the conjugate, you just change all the plus j's to minus j's and vice versa. So you have 1 minus j omega rho, okay? So when you actually work this out, it becomes 1 and then plus, and let's see here, we have omega rho squared, okay? Which is just, so 1 plus. Okay, so this is just the conjugate. So remember, this is, you know, a plus b and then a minus b. So this becomes 1 squared, or a squared, plus omega rho all squared. So that's basically what the magnitude squared would be. Okay, so that's what the magnitude squared would be. And then you have to figure out what the output process is going to be. All right, so the output process, okay, is simply the magnitude squared multiplied by the input that's coming in. Okay? All right, so we know this is 1 over 1 plus omega squared, rho squared. And this is simply sigma squared from before. Okay, so this was from the previous slide. So if you take a look here, we've already figured out what this is. So this here gets piped into over here. Okay? All right, so let's just to make this a little neat, this becomes sigma squared divided by 1 plus. Okay, alrighty. So that would be the power spectral density of the output, so that's very nice. Okay, so that's good, that's part A. Now part B asks you to figure out what the autocorrelation function is. So remember, there's a relationship between autocorrelation and power spectral densities. So if you want the autocorrelation, you just simply take the inverse Fourier of the result. Alright, so B, the autocorrelation function is simply the inverse Fourier transform of the power spectral density. Okay, so we basically have to figure out what the inverse Fourier transform of this guy would be. So this may look a little intimidating, right? So we actually don't quite know what this is. Okay, so we have this guy here. So how exactly would you go about and solve this? Well, here's a little bit of a hint. Right? In your Fourier transform table, e to the minus a, and then absolute tau, okay? This function has a Fourier transform pair, which is equal to 2a a squared plus omega squared. Okay, so if you actually take a look, if you compare, you know, this guy with this guy, we can see that there is some relationship, but you see there's an extraneous rho squared here, which I want to try to get rid of. All right. So what we can do is let's go. So we've got this, you know, so we've got rho squared. It's alpha. Sorry, it's rho squared, right? Rho squared. So therefore, I have rho squared 1 plus omega squared. Sorry, sigma squared and then 1 plus omega rho squared. Okay, that's nice. So what I'm going to do first, I'm going to do a little bit of mathematical trickery, but it's nothing that you should be uncomfortable with. So first what I'm going to do is at the bottom, I'm going to factor out a rho squared. So when I have a rho squared as the output here, then what's going to happen is that the 1 becomes a 1 divided by rho squared, which makes sense, right? Because when you factor out a rho squared, you basically have to take every single value that's inside the factoring term and you have to divide by that much. And then this becomes, whoopsie, plus omega squared. Okay, so do you see how I went from the first line to the, you know, first part to the second part? I factor out a rho squared, so in that case you have a 1 over rho. So if you were to take the rho squared and multiply this inside with every term, you're going to get what you see on the left side. Okay, so when you factor out a rho squared, you have the 1 becomes 1 over rho squared, and omega squared rho squared just becomes omega squared by itself. Okay, so I have this point. And now I'm going to do another little bit of mathematical trickery here for you. So what I'm going to do is I'm going to multiply up and down by 2 divided by rho. Okay, so why I'm actually doing this? Well, I'm going to show you why in a minute. Okay, so if I do this, this becomes sigma squared, okay, and this is 2 divided by rho, okay, divided by, and then what's going to happen is that this rho cancels with this one. So this becomes divided by 2 rho, and then 1 over rho squared plus omega squared. Okay, so actually, so if you take a look at this now, if you let a be 1 over rho, what's going to happen here? Okay, what happens if you let a be 1 over rho? So what's going to happen is we get sigma squared. The a goes on the top because it's 1 over rho, so this becomes divided by 2. And then what's going to happen is this becomes 2a divided by a squared plus omega squared. Okay, that's very nice. And there we go. So that's actually how you get it into that form. So the first step is to factor out a row squared. The second step is to multiply up and down by 2 divided by row. Because what's happening here is that you're technically multiplying up and down by 1, which you're not violating any mathematical laws. All right? So then once you do this, you factor this out, this is what we get. And then when we finally take the inverse Fourier transform, so this is what the output process would be. If you want to figure out what the output Fourier transform, the inverse Fourier transform, this is going to be A rho sigma squared divided by 2, and this becomes e to the minus a, and then tau. And remember that a was equal to 1 over rho, right? Okay, so in this case, this becomes sigma squared divided by 2 rho e to the minus absolute value tau divided by rho. And that would be your autocorrelation function. Okay? So that actually did require a little bit of mathematical trickery, but it is possible. Okay, so the first step, remember, is to factor out a rho squared on the bottom. The second step is to multiply up and down by 2 over rho. So that way, you have a rho over here that cancels out with this one over there. So you're left with 2 times rho, and then you have the rho squared over here, and then you have 2 over rho divided by 1 over rho squared. If you let a become 1 over rho, that's what you get. You take the inverse Fourier transform, this is what you get, and finally that's what you have over here. Okay, so that's actually how you do it. Okay, so a little bit of mathematical trickery, but it is possible. And finally, the last question is the average output power. That's actually very simple. So remember, there's 2 ways to compute the power. The first way is to figure out what the total area is under the curve for the power spectral density, or the next method would be taking your autocorrelation function and substituting tau is equal to 0. So let's just do the tau is equal to 0. It's easy, right? So if you want to figure out what the power is, right, it's simply taking your output process and substituting a time length of 0. So you have sigma squared 2 rho and then e to the minus 0 divided by rho, and that certainly just evaluates to 1. So this becomes sigma squared over 2 rho. And that would be the output power. Okay? And that's it. That would be the output power of your process. Okay? Any questions here? Okay, I'll give you a minute to copy that down while I actually get the next question ready. All right? Okay, so I got 1, 2, 3, 4, 1. Let me see here. And then 2, 3. Okay. All right. So you have that here. Let me just get the next question ready. So answer here. 1, 2. Okay, got 3 more. Good. All right. So let's do this one. Okay, so this would be question, what was this? This is question 4, this is question 5 now. Actually, you know what, let me not do this one first. Let me do the next one. Let me get rid of this and let me actually do question 6 first, because I think that will be a little easier to deal with. And then we'll do the next one last. Okay. All right. So now we're going to get onto noise analysis. So I think we're going to call it quits in terms of random processes for now. Let's actually take a look at noise analysis right now. Okay? All right, so we have some message signal that's comprised of 3 periodic terms. So we have a cosine term with a frequency of 1,000 hertz. The next one, which is a sine, which is a frequency of 2,000. And finally, the next one, which is a cosine of 3,000 hertz. So this signal is corrupted with an additive white Gaussian noise model. So what that means is that you have your signal and then you have additive white noise compounded on top of the actual original signal. Also, it has a power spectral density of N0 divided by 2, which is nice. That's what we're used to, and that's additive white Gaussian noise. And finally, you pass it through a low-pass filter once you go ahead and corrupt your signal with that noise. Now we're just going to take a look at just some common questions that you're going to expect on the final exam, such as, well, you know what, A, you don't really need to sketch the 2-sided spectrum. I'll do that anyway, just as review. But B and C and D are certainly applicable for what we need to deal with. So, okay, let's just do A first. So A is just basically sketching what the 2-sided line spectrum is going to be. Okay, let's go ahead and do this in F just to practice, all right? So, remember that for cosine and for sine, so for cosine, you have 2 impulses that are going to be sent. So here, F is going to be 1,000. Right? Here, F will be 2,000. Finally, here will be 3,000. So we're going to have 3 pairs of impulses that are centered at plus minus 1,000. Okay. Plus minus 2,000. And finally, plus minus 3,000. Okay. So this would be the message signal, which we'll call X. So we're going to call this X of F, and then this is an F. All right? So let's do this one by one. So we have a height of 6, right? So when you take the Fourier transform with cosine, remember you're scaling it by a half. So what's going to happen is we're going to have 2 impulses. Let's actually go up. Let me see, 6, 4, and 2, right? So let's go all the way up here. This has a height of 3. All right? Now, for sine, right, what's going to happen is that you actually have imaginary components. And not only was it going to be centered at 2,000, what's going to happen is that you have a minus as well. So what's going to happen here is that it's going to be flipped. So this will be minus 2j, and we'll call this 2j. Usually the left side has a positive impulse and the right side has a negative, but because there's a minus sign, the signs will be flipped. So you're going to have a minus down here and a plus up here. So that's your sine. And finally, for the cosine here, what's going to happen is that you have it at 3,000 and then it's going to be minus. So when you divide that by 2, it becomes 1. So you have minus 1, so you have 1 impulse here and 1 impulse here. Okay, so that's pretty much what's going to happen. So 1 impulse there. So we'll call this 1, and this is 3,000 and 3,000 there. So that's what the spectrum would look like. All right, so that's what it would look like. And then just for completeness, let's actually figure out what the power spectral density is of your noise. So just n0 over 2 for all frequencies. Okay. So just for completeness, but you don't have to. Okay. Part B, specify the fundamental frequency and the bandwidth. Okay, well, fundamental frequency. The fundamental frequency is simply the smallest possible period that would evenly divide into all these cosines, all right? So if you remember what the fundamental, at least in terms of the fundamental frequency, so omega naught is going to be the greatest common factor of the numerator, right? And the lowest common multiple of the denominator, okay? So if you actually go ahead and do that, it's just simply 2 pi times 10 to the 3. Divided by 1 if you wish, but you can go ahead and do that if you wish. So that's 2 pi times 10 to the 3. And then you have to figure out what the bandwidth is. Okay, so this is what the fundamental frequency is. So in F, it's just dividing by 2 pi, so it's just 10 to the 3. And then if you want to figure what the bandwidth is, right, it's just whatever the largest frequency value would be. So in this case, it's 3,000. You know, I can just do F of B. So in this case, the bandwidth is simply 3,000. So this is 1,000, and this is 3,000 hertz. Okay, so it's just the largest possible non-zero frequency value that you have in terms of bandwidth. It's just 3,000, at least when it's centered at 0. If you have a bandpass process, then it's just the width of whatever you have, but if it's low pass, it's from 0 to your most positive non-zero frequency. Okay. All right, so let's take a look at part C now. When you take a look at part C, determine and sketch the signal spectrum and the noise power spectral density at the low-pass filtered output. So there's a low-pass filter where the magnitude response is such that anything from 2.5 kilohertz down has a gain of 2. Anything larger becomes 0. So if you take a look, this is telling us that we have 3 different cosines, so 1,000, 2,000, 3,000. So this low-pass filter says anything from 2,500 downwards, you multiply by 2. Anything bigger is going to be 0. So what's going to happen is that you're only going to be left with two components left. So the cosine, which is at 1,000, and the sine, which is 2,000. And then the cosine at 3,000 gets filtered out because the low-pass filter bandwidth is between 0 to 2,500 hertz. Okay? So let's see here. So determine its sketch. And then also, you have to remember that you are multiplying each of the values by 2. So what's going to happen is you only have 2 pairs now instead of 3. Okay, so each of the amplitudes are going to be multiplied by 2. So in this case, we have up here and up here. This becomes 6, all right? And then the other ones, instead of 2, will become 4. So we'll have minus 4j. This is 4j up here. So 1 and 2. And that would be what it would look like after the low-pass filter. So in this case, I'll call this y. So this is sy of f, okay? And then you also have to sketch what the power spectral density would be after the low-pass filter, which is actually very simple. So remember that there's an amplitude of N0 over 2. So when you pass it through your low-pass filter, it's going to be between plus minus 2500 with a gain of 2. So N0 divided by 2 multiplied by 2 becomes N of 0. So what will happen now is that it just looks like this. So minus 2500, 2500, and this becomes N of 0 instead of N0 divided by 2, because you have a gain that is multiplying by 2, so the divide by 2 goes away and you're just left with the 2. So not the 2, you're just left with the N0 by itself. Okay, so we have that point now. Now the next question says compute the average power of the message, okay, and the average power of the output, and then the signal to noise ratio. Okay, so the average power, so remember there is no modulation. This is basically baseband transmission. So all you have to do is just simply take each of the amplitudes, square them, then divide it by 2. You don't have to do an additional divided by 2 because there's no modulation. This is just baseband transmission, okay? So for part D, if you want to figure what the input power is, it's simply, let's see here, so it's just, we have a 6, 4, and a 2. So 6 squared divided by 2 plus 4 squared divided by 2 plus 2 squared divided by 2. So we have 18 plus 8 plus 2, which becomes 28, I believe. Right? Let's see if I got that right. Yep, 28. Okay. And the, let me see here. So the average power of Y of T. Okay, so the signal to noise ratio, that's fine. Okay, so we have the input power here. And then, let's see, so input power and then average power of Y of T. So we also have to account for these. Okay, so the signal to noise, okay, that's fine. So if you want to compute what the output power is, right? So what you're doing here is you're just calculating what the output signal is going to be, okay? So it's just basically, remember, so there's just two impulses, right? So the output, if you don't consider the noise, right? So it's basically, it's just these two impulses, right? So what's going to happen is that you have your sinusoid, so this becomes 3 and then 2. All right, so let me see here, multiplying 3 and then 2. What's going on? 3 and then, so 6. So, oh, sorry. So oh, I'm sorry. So 3, 3. Oh, 6 and 4. That's fine. So let me just double check. So 3. Yes, 6. Okay, so it's 12. Okay, that's fine. So remember, because you have, so basically these two here, right? These form 12 cosine 2 pi times 1000 t, right? And these here, these ones, okay, they're going to form minus 8 sine 2 pi times 1000 t, okay? So when you have those into consideration, right, so the output power is just going to be, you'll have 12 squared divided by 2, right, because the amplitudes between here are 12, and then you finally have the 8 as well. 8 squared divided by 2. So in this case, this is 144, oopsie. So 144 divided by 2, that would be 72, and then 64 divided by 2 would be 32, and the output is just simply 104. Okay, so that would be the output signal power. Now what you do is you have to figure out what the signal to noise ratio would be. Okay, well, that's actually quite simple. So this is what the output noise is. So this is what the output noise is, right? So all you have to do is, if you want to figure what the output power is, all you have to do is just figure what the total area would be, all right? So the output power, right, is just simply what? It's just the area. So it's just 5,000 times n of 0, right? So it's just the total area of S and F. So that's simply, the width is 5,000, the height is n0. So it's just 5,000 n0. If you want to figure what the final signal to noise ratio would be, it's just simply the output power divided by the noise power, right? So the signal to noise ratio in terms of the output is simply the output power divided by the noise power. So this is 104 divided by, let's see here, so total, oh, I'm sorry, let me see, yeah, so let me see, 25, 25, yep, should be fine, twice, and yeah, so that's good, so it's just 5,000. Okay, and that's good. Okay, and that would be the total output power. So, yep, that's good. Okay, that's good here. Any questions here? Okay, good. Okay, I've actually just got 2 more questions for you, and then we're good to go. We'll be out of here very soon. Okay. I know you guys want to kill to get out of here, but the more questions I do, the better, I think. Okay, this is the second last question. right? So question 6. All right, so consider an amplitude modulated communication system. So this is actually amplitude modulation large carrier. So there is a DC offset associated with this communication system, all right? With an additive white channel noise power spectral density of N0/2, which we already know, okay? The baseband message signal is band limited to B hertz, as shown in the figure below. So this is what the Fourier transform of the input would be, okay, the input message, all right? And this is in terms of omega. All right, so we also know that the message is even, so the average value is 0. Also, we do know that the message signal is bounded by some maximum value M of P. So that's pretty much standard when you're taking a look at AMLC. So we're going to assume ideal filters in the communication path, and then the received AM signal is of this form, okay? And the demodulation is done by this signal, which is √2 cos. So what we're going to do first is we're actually going to sketch what this system looks like, because this is a lot of words. So it actually would make sense to actually sketch what this looks like. Okay, so let's actually go ahead and do that now. So before we go ahead and do that, all right, so, okay, so we're assuming that we have a modulated signal that's coming in. So what's happening is that we have a amplitude modulated signal coming in. So this is √2, and this is A plus M of T, and then this is cosine omega CT. Okay, so this signal is coming, so this is what is being sent, okay? So this is what is being sent, and then we also have a noisy signal that's being added on top, right? So once we have a noisy signal that's being added on top, we also have bandpass filters, right, to be able to filter out as much noise as we can, okay? So we have bandpass filters. Okay, so we have bandpass filters, and then we also have a demodulation side as well. So this is √2 cosine omega CT, okay? So this is used to eliminate as much noise as possible. Sorry, I can't write today. Okay, so this is your demodulation scheme, and then once you do this, you put it through a low pass filter. Okay, and then you also put it through a DC block, which is just an RC series circuit. Okay, and then the output is just your original message signal that's scaled by some scale factor K. All right, so this is what the total system would be. So you have your input. So this is your modulated signal. You have your noise added on top. All right, and then so let's see here. So we have our noise. Let's call this point here. Let's call this X of T. All right, and then after the bandpass filter, let's call this C of T. Right, and then let's call after the demodulated output. Let's call this B of T. All right. And then finally, we'll leave that to be the output. We'll call that Y, I guess. But let's have these three things here in terms of the block diagram. So if we want to figure out what the let's see here. So okay, so we have this. So before we even go ahead and do this, let's see here. So show the I'm sorry. So we have this block diagram, which will lead on to our first question. So this is part A. Show that the receiver output, the signal to noise ratio, is defined as this relationship, okay? Where sigma 0 squared, which is the output noise power, and S of 0, or in this case, our message power, is, that's how you do this. So the reason why I drew that block diagram is to solve part A. So what we need to do now is you have to go through this block diagram and then show that the output signal to noise ratio would be what is being asked of us. So let's go ahead and do each of these things one by one. So X S of T, is going to be equal to √2 A plus M of T cosine omega CT, and then you're adding noise on top, all right? So we have that there, okay? And then when you pass it through your bandpass filter, remember that the signal itself, the message signal, is going to be passed through the bandpass filter, so there's no effect. But for a random process, when you pass it through a bandpass filter, you can split it up into quadratic components, if you remember. So C of T, so the message signal passes by without any problems, but this gets split up into two quadratic components. Okay, so it gets split up there. And then what we're going to do next is at this point, b of t, we're going to demodulate by this cosine carrier, which is multiplied by root 2. So b of t is simply root 2, so we're going to do root 2 cosine omega ct times c of t. Okay? So this becomes root 2 cosine omega ct, and then you're going to multiply this by whatever c of t is. So root 2 a plus m of t cosine omega ct. Okay, and then we add this with quadrature components. So n of c cosine omega ct plus n of st sine omega ct. Okay, so that's what I have to do. So when I multiply this out, the first term, the root 2's and the root 2's cancel, so I'm left with just 2 by itself. And then I'm going to have a plus m of t, and then this is multiplied by cosine squared, okay? Okay, and then what's going to happen is that each of these terms will get multiplied by the respective cosine itself. So we get root 2 n c of t cosine squared omega ct, okay, plus root 2 n of s, and then we have cosine and sine that become multiplied. Okay? That's what happens there. All right, so that's b of t. So I'm going to do a little bit of manipulation here to get this into a form that is more familiar with us. So if there's two things that we have to remember, right? If you remember, cosine squared x is equal to a half plus a half cos 2 of x, right? And then finally, if we have 2 sine cos, this becomes sine of 2x, okay? So if I divide this by 2, this becomes a half here. So I'm going to use these two things to help me simplify this a little further. So this property I'm going to substitute into here and to here, okay? And then this property I'm going to substitute into here, okay? So when I do this, this becomes, so I have a plus m of t, okay, plus a plus m of t cosine 2 omega ct, right? Because the 2's cancel because of the half, and then I have, 1 plus cos 2 of x, so that's what's going on here. And then I can do the same thing on this side as well. So when I divide by 2, root 2 divided by 2 is simply 1 over root 2. So this becomes 1 over root 2 nc of t plus 1 over root 2 nc of t, and then cos of square omega. Let me just move this over. Okay, and then cos of 2 omega ct. So that's that part. And then finally I have this one over here. So cosine becomes sine 2, and then when I divide by 2 again, I get 1 over root 2. So 1 over root 2 ns of t sine 2 omega ct. Okay, so we have b here. So now what's going to happen is that after you put it through the low pass filter, remember it's bounded between minus and plus b. So anything that is modulated by the carrier gets canceled out, also the DC block as well. So after LPF and DC block, okay, there's going to be two things that are happening. So after this here, what will happen is, so after the LPF, what's going to happen is that this goes away, right? This goes away, and that goes away. And then after the DC block, this goes away. So therefore, our final output signal is simply m of t plus 1 over root 2 nc of t. Okay, so that's going to be the output. All right, so let's go ahead and figure out what the output signal to noise ratio is. So the signal power is going to be just this guy here. So it's the expected value of whatever the message is. So in this case here, it's just equal to whatever the message signal was to begin with. And now if you want to figure what the noise power is, it's actually very simple. So this is the expected value of 1 over root 2 nc of t. So this is all squared. Okay, so this is equal to 1/2 expected value nc of squared. And that's simply equal, if you remember the quadrature components, is just equal to the actual noise power itself. So this is just 1/2 sigma squared, output squared. All right, so this, if you recall from, let's see here. So actually, we'll go ahead and do that right now. So whatever the output power is. So if you remember, let me see here. So the, what was it? So once you pass it, so you have a bandpass filter and then you push it through the low pass filter, right? What's going to happen is, not low pass filter, but the outputs, you have your DC block. What'll happen is that the power spectral density is going to look like this, right? So it's going to go, so it's between minus B to B, sorry, not minus B to B, but your bandpass filter basically looks like this, right? So the width here is 2B, right? The width here is 2B, and this is N0 over 2. So this is what the input, this is what the input power is going to be. So this is the output power by itself. Okay, so if you actually figure what this total area is, therefore the total area is just simply whatever this twice as much. So this is 2N0B. So therefore, the actual total signal power, not signal power, the noise power is half of 2N0B, which is just that by itself. So that is actually covered in the lectures, but I just wanted to put this here for self-containment. So now that you have this, therefore the actual signal to noise ratio, the output, is simply the message divided by N0B. Or in this case, it's just whatever the signal power is divided by whatever the noise power is, and that's what we have. So this is here, and then this is from before, so where is it? This is over here. All right, so that would be, that's proving the, that's just going through the entire chain through signal to noise ratio. All right, so the next question, B, if the bandwidth is 20,000 hertz, okay, and N0 is 10 to the minus 7, determine the receiver output. Okay, well that's pretty simple, all right? So, let's see here. So the total power is, yeah, that's fine. Okay, so the total message power, that's fine. Da, 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 da. Okay, yeah, I'm just taking a look at my notes just to be sure that I'm not crossing myself. Okay, let's go to the next slide. Okay, so this is what our signal power would be. So this is what the message power is, not the message, this is what the power spectral density of the message would be. So if you want to figure out what the total power is, all you have to do is figure out what the total area of this would be. So you have to figure, so let me see, so determine the output receiver, so N07, bandwidth is 20,000, so you have to figure out what the total power would be. So we know that the total power is N0B, right? So all you have to do is just figure that out and you have to solve for what that power would be. So, let's see here. So if B was 20,000, okay, so what's going to happen is that it's going to look like this. So it looks like this, right? This is 10 to the minus 4, okay? And if B is 20,000, then what's going to happen is this becomes minus 40,000 pi. Okay, this is part B, and this is 40,000 pi over here. Okay, so this is 40,000 pi. All right? So if you want to figure out what the total power is, or what you have to do is you can just consider this as basically just two triangles that are just added together, right? So all you have to do is just figure out what this total area is and just multiply that by 2. So what's the area of this guy here? So you know that this here is 10 to the minus 4 and this here is 40,000 pi, right? And also this is in terms of omega. So what you have to do is you have to also divide by 1 over 2 pi as well. So the output power in terms of the message, right? Okay, the output power, sorry. It's going to be 1 over 2 pi because this is dealing with omega. Then you have twice, and then whatever the area of this triangle would be. So this is a half times 40,000 pi, right? Times, whoops. Okay, good. I'm going to leave it like that. So times 10 to the minus 4. Okay, so these 2's cancel. This pi cancels with that. Okay, so then finally we're left with 20,000. Times 10 to the minus 4. So that would be the message power, okay? Also the noise power, so this is what the message power would be, right? So I'm not P of M, let's call this S of 0, all right? Also the noise power, we know it's simply N0B, right? In this case, this is 10 to the minus 7 times B, okay? Which is going to be 20,000, right? So 20,000. Okay, so that would be it. So if you want to figure what your signal to noise ratio is, okay, all you have to do is just take the output power, which is 20,000 times 10 to the minus 4, divided by, and this is 10 to the minus 7 times 20,000, right? Actually, the 20,000 will cancel, right? And then you're left with 10 to the 3, right? Which is going to be 1,000 in terms of volts to volt. If you want to figure this out in terms of decibels, you just have to take 10 log, 10 log 10 of whatever. So if you want to figure out what the signal to noise ratio is in decibels, you just take 10 log 10 times 10,000, not 10,000, 1,000. Log 10 of 1,000 is simply equal to 3, so this would be 30 decibels as the output. Okay, and that's what the output would be. All right. Okay, so that's 30 decibels there. What's next? Okay, so done this, done that. It is useful to compare the performance of different modulation schemes with equal received signal power. For AM systems, show that the output signal is upper bounded by this relationship. So the output signal to noise ratio is bounded by gamma over k, where k is equal to 1 plus mu to the minus 2. With modulation index mu, and gamma is equal to your canonical baseband power. Okay, that's totally fine. We can certainly do that. So C. Okay, so you know that the signal to noise ratio, okay, is simply, what is it? It's Sm divided by N0B. And if you remember from the lectures, if I multiply up and down by N0B, not M, but by, multiply up and down by Si, okay, the input signal power, right, this is equal to A squared plus Sm squared, okay? The reason why that is I'll let you refer to the lecture notes. So I'll let you go. I want to finish quickly here. So I'll ask you to refer to module 10 slides. Okay, so the actual input signal power is actually just the amplitude squared plus the whatever the message signal squared would be. So this here we know is gamma, right? So this means that this becomes Sm divided by A squared over Sm. And this becomes gamma. All right, so now that we have this, what I can do is I can go a little further. I can actually divide up and down by Sm. Okay, so when I do that, so this becomes 1 divided by A squared over Sm plus 1, and then multiplied by your gamma there. Okay, and then we do know the fact that from amplitude modulation, we know that mu is equal to the maximum peak divided by the amplitude, okay? So if I did mu squared, this becomes mp squared divided by a squared, and if I take the inverse to the minus 2, I'm just simply finding the reciprocal, so this is a squared divided by mp squared. Okay, so I'm gonna use that, I'm gonna exploit that with this derivation over here. Okay, so here's a little bit of a relationship to take notice of. So we do know the fact that the largest possible value, either plus or minus, this relationship is given to us. We know that this is given by the question, okay? So if I were to take the squareds of both sides, right, so if I took this squared, I'd still know that this is gonna be less than the message peak squared, okay? So I do know the fact that, okay, so if I take the expected value of both sides, right? If I take the expected value of both sides, what's gonna happen? Well, this becomes S of m, and then the expected value of a constant is just mp squared, all right? So once I know this, I can use this and exploit this with my derivation. So let's go over here, all right? So this becomes, so I have 1 divided by a squared divided by Sm plus 1, okay, gamma, and then if I can use this relationship and bring this over here, so this is gonna be less than 1 divided by, let's see here. Let's see, so we have 1 plus mu to the minus 2. Okay, so that's what's going on. So I can actually use this relationship to bound this. So let's see here. Because I know for the fact that the maximum peak is going to be m of p, so I know that if I use this relationship, if I let if I let Sm be m of p, so what's happening here is that I can change this and I can replace S of m with mp of squared, and then I can use this and tie this into here, and this is what I get. So that's the relationship that I get, and then I multiply this by gamma. Okay? So, and then if you take a look at the question, it says gamma is equal to, not gamma, sorry, it's k is equal to this guy over here. So I just have to replace that and then I'm done. So therefore, let me see here, what's going on here. So the signal to noise ratio, okay, is going to be bounded by, let's see here, okay, where k is equal to 1 plus mu to the minus 2. All right, so we have this relationship now, and we're pretty much done. Okay, so part D, let's take a look at part D. So what does the maximum achievable output in terms of gamma? So how does this compare with DSBSC? Okay, so if you remember, for amplitude modulation, we know that the modulation index spans between 0 and 1, okay? So therefore, if mu is equal to 1, this is the maximum possible SNR to get. Okay, so in that case, if you get mu is equal to 1, K is simply going to be 2, which means that the output signal to noise ratio is going to be gamma divided by 2. It's going to be bounded by gamma divided by 2. And then if you were to take the decibels of this, right, so in dB, this is equal to 10 log 10. Gamma plus 10 log 10 a half, which this case is minus 3 decibels. So this tells us that the performance is actually 3 dB worse in comparison to your standard double sideband suppress carrier. So therefore, amplitude modulation LC, the large carrier scheme, performs 3 decibels worse than the standard double sideband suppress carrier. Okay, and that's pretty much it there. All right, so yeah, this was a little more theoretical. I just wanted to do this as an exercise, just to make sure you actually know what's going on. But that's pretty much it here. And I have one last question, and then we're going to call it quits. Okay, this is my last question for you. We'll be out of here soon, I promise. 7. I figured I'd do more questions, but keep you here a little longer. That way you get practice for the final exam. All right, so this is my last question, and then we're going to call it quits. All right, so, okay, so we have the following block diagram that is concerned with demodulating a double sideband suppressed carrier signal. That, you know, your DSBSC signals of the form MFT coast, right? Where MFT is a baseband modulating signal that is band limited to BM hertz. So the bandwidth of this signal is bounded by B of M, okay? And the average power is P of M, and then FC is the carrier frequency, and we know for a fact that the carrier frequency is going to be much bigger than the bandwidth of your message, which makes sense. That's standard for any DSBSC's modulation scheme. We also have a white noise process in terms of the noise that's coming in, with a power spectral density of N over 2, or N0 over 2, which is what we expect. It's your additive white Gaussian noise process. Okay, that's great. So this basically shows you a modulation and demodulation scheme that is associated with this stuff here. So you have your message, you have a modulated signal coming in, which is going on here. You add noise. You have a bandpass filter that filters out as much noise as you can. You demodulate. You put a low-pass filter to get rid of all the sideband components. You just want the baseband, and then you're done. And the magnitude squared response so the bandpass filter is not an ideal bandpass filter. It looks like this. So it's basically triangular, and it's only shown for positive sides only. Okay. The filter represented by HL of omega, which is this guy over here. So it's a low-pass filter where it's a unity gain with a cutoff frequency of B of X such that it is between the bandwidth of your message and twice the bandwidth of the message. So it's bounded. It's a variable low-pass cutoff that is bounded between the bandwidth of your message and twice the bandwidth. Okay, so we're going to go ahead and calculate all this stuff here. So part A, so let N I of T be a band-limited noise process of the output of the bandpass filter. Determine the power spectral density and whatever the average power would be. Okay, well that's pretty simple. Take a look that they give you the magnitude squared, which is very nice. So the output, right, the output message, so the determine SI, so the output, we're going to do this in terms of F, just to be simple here, okay? So they want to figure out what the so the output of the bandpass filter. So it's basically going to be the magnitude squared of your bandpass filter, so magnitude squared, multiplied by whatever the input is coming in. In this case, we're going to call this Sn of F. Okay? All right. So, because this is already squared, all you have to do is simply take your noise process and just multiply everything by N0 over 2. It's already squared, so it's actually very nicely done. So, we're just going to take a look at the positive side for now. So, it's going to look like this. Okay? This is the output of the noise. Sorry. So, it looks like a triangle like that. and then between here and here, this is, let me see here, so f of c minus 4bm, f of c minus 2bm, f of c plus 2bm, and f of c plus 4bm. So b of m is the bandwidth of your message, okay? And then this is your frequency. This is just positive only, all right? So that would be pretty much what this power spectral density looks like, and this is scaled by n0 over 2. Next question. So determine the average power. Okay, that's pretty simple. Okay, so if you want to figure out what the average power is, it's very simple. So I'm going to actually do a shortcut here. So we got to figure out 3 pieces. So we have to figure out so when you're finding the area, you have to figure out what the area of this guy is, the area of this guy is, and the area of this guy. So remember that you can actually take 2 triangles and you can piece them in such a way where if you piece 2 triangles together that are of equal width and height, it's just a square, right? So what I could do is I can take this guy and flip it so that it comes like this, right? So I can flip like that. So basically what's going to happen here is that if I want to figure out what the total area is, I just have to figure out what the total area of this rectangle is, because what I can do is I can take this triangle and shift it so that it goes over here, because I'm trying to find the total area. I don't care what it looks like. I'm trying to find out what the total area that is occupied by this would be. So if I took that triangle and if I rotate it and put it right on top of the other one, that would basically be a square. So you have a rectangle and a square together, and I want to find the total area of that entire rectangle. Okay? So therefore, I just have to figure out what the total area is. So this is NIF squared. So basically what I have to do is I have to figure out the area of this guy over here. So it's going to go between, so this here would be FC of minus 2bm, right? And this is FC of plus 4bm, okay? So then you have this here, right? So this is FC minus 2bm, and then you have 2 triangles here, like this and this, right? So it's basically just finding this total area. So this is n0 over 2, so what is it? It's width times height, right? So the total area, right, is simply n0 over 2, right, multiplied by the width here. So the width is just 6b of m, right? So let's see here. So not n of 0 over 2, it's just 1. Let me see here. So n0 over 2, 6n, yep. So n0 over 2, that's fine. Just want to double check here. N0 over 2, that's good. So the width, so it's twice and 2 pi, so 6. Height, I think I screwed up. Okay, that's fine, that's fine. So the height here, so n0 over 2 multiplied by, and then this becomes 6. Right, so this is just 3 and 0 b of m, right? So the height here is n0 over 2. The width between here and here is just 6 as much. Because what you're doing is you're taking this triangle and you're putting it over here. So this is from 2 to 4. So you're just finding what the area of that rectangle would be, which is just 3 and 0 b of m. All right? So that's just one piece, but then you have to add, remember, this is just the positive side, so you also have to multiply by 2 because you have the other area on the other side as well, right? So what's going to happen is you also have this from here to here, from here, right? So this is just, so the total area here, so what's going to happen, it's going to be twice this much, okay? So you actually have this area to consider as well. So you have 1, and then you have 2, right? Because you have twice as much. So what's going to happen is you'll have 2 times, and then the height will be n0 over 2, and then multiplied by the width, which is 6b of m. Okay, so these cancel, so you're left with 6 n0 b of m. Sorry, I forgot to account for the other half as well, because remember, you're only showing the positive side. So if you want to calculate the total area, remember, you're finding the integral from minus infinity to infinity. So you have the negative side to encounter and the positive side to encounter. So that's why you have to multiply by 2. In that case, you finally have your total output area to be 6 n0 of b of m. Okay? All right, so part B, determine the time domain expressions for yi and y0. Indicate the reasoning you use to arrive at these expressions. Okay, that's fine. So, let's see here. So we have this system here, so we have to figure out what this is and what that is. Okay, so what's going on here is that you have your modulated signal, you add your noise on top, you put it through your bandpass filter, and then you get the output. So let's actually figure out what's going on right over here. Let's call this C of t. Okay? So C of t, so this is part B now. C of t is equal to the message signal is coming in, so it's DSBSC, so M of t, cosine omega ct plus N of t. So that's what's going on right now. So you add the noise on top. And then you also have to apply your bandpass filter on top of this as well. So remember, your message signal, this here, is going to be bounded between what? So if theoretically it'll look something like this maybe. So it looks like this, right? So and then it looks like this, right? So this is your carrier, and this is FC plus B of M, and this is FC minus B of M, and then the same thing on this side. Okay, so that's what's going on right now. Okay, so when you put this through your bandpass filter, what's going to happen is that notice that it's going to be, you know, minus and plus. So if you take a look at your characteristics of your bandpass filter, what's going to happen is that B of M is simply going to be between here and here. So this is FC minus B of M, and this is FC plus B of M. So if you put this through your bandpass filter, notice that the height is going to be 1. So when you actually put your signal through your bandpass filter, this simply will just be equal to the message itself. All right. So yi of t, in this case, your message signal is just going to be the same. All right. So yi of t, it's going to be m of t cos. Okay. So that doesn't change, but the noise is going to change. All right. Because what will happen is that, remember, when you put it through your bandpass filter, all right, what's going to happen is that you'll have this splits up into 2 quadratic components. Sorry, this is NC of t, M of S. And then N S of t. Okay, so we have that expression. So now we have to figure out what the output message is going to be. So with the output message, so you have your bandpass, and then you modulate by cos, and then you put it through your low pass filter again. So let's see. So we have that. That's fine. And so we have to figure out what the output message is going to be. So all you have to do is just take your yi of t and multiply that by 2 cos. Okay, so that's good. So we're just going to let this be omega ct just to make things a little easy. So this becomes cosine omega ct, right? So whatever this is, and then finally we'll multiply this through. So this becomes 2 m of t cosine squared omega ct, okay, and then plus 2 nc of t cosine squared, okay, and then plus 2 ns of t sine cos. Okay. All right, so we have this now. So let's go ahead and simplify this a little more. So we're going to use the cosine and sine squared terms that we had before. So this is m of t plus m of t cosine 2 omega ct, right? This becomes nc of t plus nc of t cos of 2. So I'm just using those trigonometric formulas again. And this becomes plus ns sine 2 omega ct. Okay, so that's where you get that from. And then when we finally apply your bandpass filter, what's going to happen is that, so after the bandpass, so this is, and then so we have this, and then we have to make sure that this is filtered by our low pass filter, all right? Okay, so this is filtered by your low pass filter. So once you go ahead and do the low pass filter, what will happen is that this term goes away, this term goes away, and that term goes away. So we're finally left with m of t and then plus nc of t, and we're done. Okay, this is nc of t, and then also it's low pass filtered. So I like to point the fact out that this is low pass filtered, because this noisy signal is, you know, it's low pass filtered. So this noisy signal exists for all frequency values. So I just want to make sure that to tell you that this is low pass filtered. Okay, all right. So that's part. So determine the input and output signal to noise ratio at the outputs of the bandpass filter and the low pass filter respectively. Okay, that's pretty simple to do. Okay, so the input, if you remember, it was simply m of t cosine omega ct plus, and then the input signal that's coming in, right? Ni of t, I think, right? Not n of I, but input, yeah. Okay, so I think that's good. So on low pass filter, let me see. So this, let me see here. Let me see what's going on quickly. Yeah, that's fine. Okay, that's good. Sure. All right. So that's the input that's coming in, and then let's see. I'm just double checking. So SNR, I, and O. So input signal is coming in. So outputs of the bandpass filter. Okay, so bandpass filter, quadratic components is totally fine. Okay, so we have that. Okay, so we have these components now. Let me just double check yi of t. Okay, so nc and then n of s. All right. So this is equal to nc of t cosine. Just want to simplify this a little bit. Okay, so this here is your signal, right? And this here is your noise. So if you want to figure out what the signal to noise ratio is for the input, right? It's simply your signal power divided by your noise power. So this here, right, your signal power, right, would be just the average value squared divided by 2 because we're modulating by your, we're modulating by the actual signal by itself, right? So in this case, this becomes m squared, whatever this is, divided by 2. And then you divide this by whatever the noise power would be. So we've already calculated that. This is equal to 6n0 b of m. In this case, we finally get 12n0 b of m. Okay, so that would be the input signal to noise ratio. Now you got to figure out what the output is. Pretty simple. Okay, so let's figure out what the actual, this here is equal to m of t, and then plus, this is low pass filtered. Okay, so the signal power is very easy. It's just, m of, s of m, I guess, right? So we'll just call this m squared, right? Because you're not modulating by anything. And then the output power is pretty simple here. So it's just the output of the low pass filter, right? So what's happening here is that it's going to look like this, right? So this is your output, and then the it's bounded by b of x. So this is going to be between here, and then it's also variable. So, it can actually go up to here if you wish. Not b of x, but b of m. So it's actually a variable low pass filter. So this is the smallest value, and then twice b of m would be the largest value. So it's actually variable, right? So let's just call this value b of x. Okay, so let the bandwidth be b of x. Okay, so in this case, we'll just call this, so whatever this area is, okay, so in this case, this is just equal to 1. Not 1, but when you pass it through a low pass filter, this is scaled by n0 over 2. Okay, and then when you actually find what the total area would be, okay, so let's see here, n squared low pass filter twice. Yep. So you're basically just finding what this total area would be. So it's just twice times that, so this would becomes 2 times b of m, and then n0 over 2, which is just n0 b of, not b of m, but b of x. Okay, so that's what happened here. And then finally, if you want to figure out what your signal to noise ratio is, it's very simple. So it's just equals, so m squared divided by, okay, so there we go, so twice, yep. Okay, so that would be the actual value. And then last but not least, determine b of x that'll maximize the SNR. So basically, if you want to maximize the SNR, what you have to do is you have to make sure that this value is as small as possible. So that's how you maximize the SNR. So when the denominator is small, the SNR is going to be big. So therefore, maximize SNR is making n0 b of x small. And the smallest possible value would just be b of m. Therefore, b of x is simply b of m. So therefore, it's just this. M squared of t, and then n0 b of m. All right, and that's it. Yeah, this is a little more complicated than usual, but I wanted to make sure that you have questions that vary between all difficulties. Okay, that's it, guys. Sorry to keep you so long, but that's it. So remember, Wednesday there is no class. Do not show up. I will not be here. So if you have questions regarding your midterm marks, I guess, or if you have questions regarding the tutorial, anything that deals with the course, then just send me an email. I will certainly email you back. And then the next time I will see you is next Monday, ENG LG 11 downstairs for a final exam. Okay, so I wish you all the best. Good luck studying, and I'll see you next Monday. Thanks.